Start.
Well, welcome to Rogue Squadron. Our group is called Rogue Squadron, and this is the Battle of Endor. I'm Daniel Clyde.
I'm William Black.
Alexander Whitelock.
And I'm Logan Scoville. So you can see our game right here. The basic premise is we have an X-Wing and a TIE fighter doing battle. You can choose to fire a laser from either side of your ship that will go forwards, or you can drop a bomb out the back of your ship that will do much more damage, but it's a lot slower moving. And once one player loses all of their health, then the ships reset their positions and the lives will decrement. And once the player loses all of their lives, then the game is over, and you can choose to play another game. Now, as far as the mechanics of the game, we have a game loop running, and inside the game loop we call functions that will do all of the input and output and all of the logic for our game, as well as anything else that needs to be done. It'll do collision checks, etc. And we wrote this all in our own custom assembly language, and that compiled down into about 6,000 lines of machine code. We could have optimized to make it fewer lines, but we chose to favor our time over the amount of memory that we use, because we had quite a bit of wiggle room for memory. So now that that's covered, I'm going to turn it over to Alex, and he's going to tell us about the assembler.
So in order to write the game, we wrote our own assembler, and we added several other things that would allow us to do some pseudo instructions. So one of the things that we did was we made it so that you could do immediates that were 16 bits instead of the 8-bit immediates. And in order to do this, you would load in the upper, load in the lower, shift them over and order them together. This was all done inside the assembler, so you could just say load word immediate 4000 and it would work. Another thing that we did is we added labels. Let me show you over here. We had to kind of allocate some specific registers in order to make the assembler really work. And so we designated 13 and 14 were used for those pseudo instructions, and then our 12 was used for linking. So somebody could write labels in the assembly code, and you could say, okay, jump to this method, and then the R12 word store would have the return address, and so after the method you would jump back to where we were, and the code could kind of go sequentially but also jump to methods. Daniel's going to talk a little bit more now about how we separated memory and handled those different issues.
Okay.
So as he talked about, we have these dedicated registers for pointing to our heap. We call it the heap, but it's a block RAM within the FPGA. We organized our heap in a way so that we could have assembly instructions first, then the frame buffer, which basically keeps track of what's on the screen inside the computer, and then we also had our glyph library, which makes up each fighter and each torpedo, each laser, and each glyph. And after that, we had memory devoted to the actual X-Wing and the TIE fighter. So this information, if you can see, the yellow keeps track of their position, the red keeps track of their health and their lives, the blue keeps track of their weapon systems, and the green keeps track of where their lasers are, so we can keep track of who hit what, who hit where, and decrement lights accordingly. We had these registers here that could point to the return value. The glyph pointer was a little bit of this, and then this R11 points to the top of this struct here, so that we can navigate through memory really easily. Yeah.
I'm going to talk about the underlying architecture of the processor. So the basic processor is a 16-bit single-cycle processor. And essentially what it's doing is our processor is constantly loading in instructions from memory by incrementing the PC counter by 1 every time. And then unless we do a jump, and then we can jump through memory to get to the proper instructions that we need to execute for our game code. And our processor also implements a few extra peripherals for the NES controllers. The NES controllers go into a module that refreshes every 60 hertz, on a 60 hertz cycle, pretty much pulling the input. So, and what we do in our processors, we created a set of some instructions that allow us, the programmer, to pull in the inputs whenever we want with a simple LIO instruction that allows us to put it into a register. And yeah, and that that works, then all of our entire processor is really controlled by it's the control unit, and it's really just a finite state machine that goes through some basic states, a fetch state to a decode state, and once it's in the decode state, it can go to any numerous state, either the R-type instructions where it'll do like an add or an OR instruction, store instructions to store data into memory, branch instructions, I-type, which are very similar to R-type, shift instructions, jump instructions, and load instructions. And load allows us to load from memory, which is key to our game. And that's the basic setup of our processor. All in all, it just works, and the game is over now, and we had a winner. Our Rebels pulled through.